Hi, so today we're going to look at a really relevant problem, especially in classical mechanics, because it shows how the way mass is distributed can completely change how a body rotates. We're looking at a homogeneous cylinder of mass m, radius alpha, and length L, but with a small cylindrical cavity cut out, tangent to and parallel with its main axis, which is the z-axis. This makes the cylinder non-uniform, which means its center of mass and moment of inertia are no longer obvious. So our tasks are first, figuring out the distance from the original axis to the new center of mass axis. Second, calculating the moment of inertia around both axes. And finally, if the cylinder rolls without slipping, determining its total kinetic energy in terms of theta, where theta is the angle between the vertical and the line connecting the cylinder's center to the cavity. Also, please take note that to solve this problem, you don't need to do any integrals. And let's jump right into it with the first question.
So, as you probably know, when coming across those kind of problem, the first thing you want to do is draw your system because it's going to help you visualize everything else much better after that. So, your system should look like this. So we have a initial cylinder, which we remove a cavity, and we place that cavity tangent and parallel to the axis of symmetry that we called Z of the initial cylinder. In this statement, we know that the mass of the initial cylinder, M1, is M, and its radius is alpha, and the radius of the cavity is equal to alpha divided by 4. Okay, so since the statement explicitly says that we do not need to use any integrals, we can use a shortcut. And the shortcut is equation 4.69 of David Morin's book, which says that the vector position of the center of mass relative to our frame of reference, it's important to note that this is our frame of reference. So the position of the center of mass is equal to the sum of each individual mass multiplied by their own position of center of mass relative to our frame of reference divided by the total mass of the system. So in our case, it's m1 multiplied by the vector position of the center of mass of our initial cylinder minus, here it's minus, right? Because we are removing a portion of the initial cylinder. Minus m2 multiplied by the vector position of the center of mass of the cavity divided by the total mass, which is in our case m1 minus, don't forget we are removing a portion of the initial cylinder, so minus m2. So let's call this equation number 1. So we have our equation, and now let's find our ingredients. So we have most of them. We have m1, which is equal to m. We have r1, which is equal to 0, right? Because that's how we place our frame of reference. We place our frame of reference at the center of mass of our initial cylinder. Now, for R2, let's draw the top view of this. So let's draw this portion here, looking on the top of it. So we have the big cylinder, which is centered at its own center of mass. And we have the cavity here. So if we think at the cavity as a solid, the center of mass of that solid will be at the axis of symmetry of the cylinder. So the distance right here is just R2 here. So R2, vector position of the center of mass of the second cylinder relative to our frame of reference will be alpha divided by 4 in the x direction and 0 in the y and z direction. Now, for M2, we don't know it yet. So let's find M2. To do that, we're going to use the fact that the mass of any cylinder is equal to its density multiplied by its volume. And this is equal to density multiplied by pi, the radius of the cylinder square multiplied by its length. Therefore, so this is the sign for therefore. This is a mathematical sign for therefore. So if you see this, it's mean therefore. Therefore, M1 is equal to the density pi alpha square L, and M2 is equal to the density pi alpha divided by 4 square L. This is equation number 2, and this is equation number 3. Here we can assume that both density are equal because the first cylinder comes from, actually no, the second cylinder comes from the first cylinder, and this is a homogeneous cylinder, so both density must be equal by definition. So here we have two equations for one unknown, which is M2, because we know that M1 is just equal to M. So from equation number 2, we can say that the density is equal to M1 divided by pi alpha square L, and we can put this in equation number 3. We will have that M2 is equal to M1 divided by pi alpha square L multiplied by pi alpha divided by 4 square L. And now we can simplify. This goes away, this goes away, bye-bye, bye-bye, bye-bye. So this is going to be equal to M1, which is M, divided by 4 square, which is 16. So M2 is equal to M divided by 16. So now we have all of our ingredients to solve equation number 1. So let's just do that. So the position vector of the center of mass is equal to M1, which is M, multiplied by R1, which is 0, minus, don't forget minus, M2, multiplied by R2, which is alpha divided by 4 in the x direction and 0 in the y and z direction, divided by the total mass, which is just M1 minus M2. Now we can solve this. 0 this goes away. This is equal to 15 divided by 16. 16 goes away. So we have the vector position of the center of mass relative to our frame of reference. This is alpha divided by 4 multiplied by 15, which is 60, in the x direction, and in the y and z direction is just 0. So we can say that the distance from the z-axis to the center of mass is alpha divided by 60. So here you have it. We just solve the first question. So the trick here is really to use the fact that in the problem it says that we do not need to use any integrals. So we can just use the equation for the vector position of the center of mass and look at the problem as two different solids.
In B, we're asked to calculate the moment of inertia of this rigid body with respect to the z and z prime axis. The z-axis is the one that passes through the geometrical center of the cylinder, and the z prime axis is the one that passes through the center of mass of the cylinder. To solve this, we'll use the parallel axis theorem, which basically says that if you know or find the moment of inertia of the system at its center of mass, you can find the moment of inertia about any other axis parallel to the center of mass axis by adding the total mass of the body multiplied by the square of the distance between the two axes. So here it's r. R is the distance between those two axes, okay? Please, not to be confused with the radius. In some books, you'll see R as D or vice versa. It really depends on the writer. So let's jump right into it. First of all, we will need all the information we got from A. So the mass of the second cylinder and the distance between Z prime and Z. We will also need two equations. The first one is the moment of inertia of a cylinder, and we will also need the parallel axis theorem. So to find the moment of inertia around Z, here, we will use the same logic that we use in A. So the moment of inertia around Z is equal to the moment of inertia around Z of the first cylinder minus the moment of inertia around Z of the second cylinder here. So the main part here is to figure out which equation do we use. So for the moment of inertia at Z of the first cylinder, since the z-axis passes through the center of mass of our cylinder, we'll use the first equation. So this is equal to m alpha squared divided by 2. For the second cylinder, we can see that the z-axis does not pass through the center of mass of
our smaller cylinder. This is the axis that actually passes through the center of mass of the second cylinder. So we will need to use the parallel axis theorem. So equation number 2. So this will be equal to the mass of the second cylinder, which is divided by 16 multiplied by d. So d here is the distance between both of our axes. So in our case, it's just R2. So multiplied by alpha divided by 4 square plus the moment of inertia around the axis that passes through the center of mass, which is just the equation number 1. So plus 2, which is divided by 16, multiplied by the radius 2, which is alpha divided by 4 squared divided by 2. So we can just reduce the equation now. So we already found the moment of inertia of the full system around the z-axis. Now let's move on to the moment of inertia around the z-prime axis, which is right here. Actually, we don't even need to draw it for the other cylinder. We can actually just use the equation number 2 because we already have this, so we can isolate the moment of inertia around the center of mass because the z prime axis is at the center of mass. So we can say from equation number 2 that the moment of inertia at the center of mass is equal to the moment of inertia of z prime, which is actually equal to the moment of inertia around z minus the mass of the full system. In our case, the full system is m minus m divided by 16, right? Because we are removing this cylinder from the initial cylinder. And then multiplied by d squared. So like I said before, remember d squared is just the distance from both axes. So in our case, it's b. So it'll be minus b squared. And this is just this. So we will have that this is equal to m alpha squared multiplied by 253 divided by 515 minus 15 divided by 16 multiplied by b squared. So just like that, we found the moment of inertia around the z prime axis.
So in C, the body rolls on its side without slipping on a horizontal plane. We're asked to calculate the total kinetic energy and express it as a function of theta and the derivative of theta, where theta is the angle between the vertical and the line connecting the center of the original cylinder and the center of the cavity. The kinetic energy of that kind of system is given by kinetic energy at the center of mass plus, not at the center, but of the center of mass, plus the kinetic energy from the rotation. And this is equal to half of the speed of the center of mass squared multiplied by the mass of the system plus half of the moment of inertia around the center of mass multiplied by the angular momentum squared. So this is a really useful equation that you want to keep close by. So what we have here. So we already found this from the previous number. It's just equal to the moment of inertia around z prime. The angular momentum is the derivative of theta. The mass, don't forget, the mass is not m in our case because we remove a cavity of the cylinder. So m in our case will be equal to 15 divided by 16m. So we're only missing the speed of the center of mass. Since the center of mass is shift to the left, we cannot just say that the speed is equal to r theta dot. Okay? We have to find the vector position and then take the derivative of it, and then we can find v squared, because v squared is equal to the derivative of the center of mass, of the vector position of the center of mass. So let's find the vector position of the center of mass. So if we draw our system, we have our cylinder on its side. Something like that. This is just another x-axis, just to visualize the rotation, okay? We're not going to use this x-axis in our calculation. It's this one we're going to use in our calculation. This is just to visualize the movement of the center of mass. So the center of mass is about here, and this is the geometrical center of our cylinder. So when it's going to be rolling, the center of mass will move up and down and up and down as well on the y-axis. You can see it. Go up, down, 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 down. It goes to the minimum, and then it goes right back up. And it does the same for, about the same for the x-axis, right? Because it goes left to the x and right to the x, and it's just do that over and over again. And since it's rolling without slipping, it's also moving on the side.
And this position, we already know that the movement to the right is equal to x equal to r theta. So yeah, so this would be if the center of mass would be at at the geometrical center, we will have x is equal to this and y is just equal to r. But in our case, it's different because the center of mass will move something like this, right? Okay. So we need to find this vector at all time. Not at all time, but at all thetas. So let's draw the vector. It's this one that we're looking for. And let's draw theta. So this is the cavity, about like this. And theta in the problem, it says that it's this here. Okay, so to find the position of the center of mass, we'll use a vectorial analysis because we know that this is just r, the vector r, and this is b right here. And if we add vector r plus vector b, we will get the position at the center of mass at all thetas. So let's find the vector b. So for b, it's like this. This is theta as well because of this symmetry. Okay. So we see that b sine theta is equal to x and b cos theta is equal to y. Here I use the full angle just to make sure we get the right positive or negative. If we had used theta minus 90 degree, we would have to figure out what's the plus and the minus. So it's just an easier way to calculate the x and y. You always want to look at the angle from the x-axis to your vector. It's just a little trick. You can just use this angle as well. It's up to you. Okay, so we found our vector for b equal to this. Okay, now for the vector r, r is quite easy. It's just like this. In the y direction. However, it is moving in the x direction as well because it's the cylinder is not slipping, so it's going to do like this. So the vector r will be equal to r theta in the x-axis and just r on the y-axis. So the position of the center of mass is equal to vector b plus vector r. It's equal to this. Okay, so now we want to find the speed. The speed is just like we said before, the derivative of the position. So this is equal to cos theta and the derivative of theta plus r and derivative of theta. Oh, here we forget plus r here. Okay, so this is minus r b sine theta dot. Okay, and we need v squared, which is equal to this, and it's equal to. So here, when we're going to put it square, there's going to be a cos square, and there's going to be a sin square. There's a r here that it's not good. There's no r here. I don't know where it came from. There shouldn't be any r, right? Because we're not multiplying them, we're just adding them. So this is b and b here. Okay, so like I was saying, when we're gonna put this square, there's gonna be cos square, sine square, adding together, which is just 1. So we can already see that we have theta dot squared multiplied by b squared, and then after we will have plus 2br cos theta. This is from having this squared, and then plus r squared. So we have our speed at the center of mass. Let's just put the value of b, which is alpha divided by 60. B squared is this. However, just b, don't forget, b is equal to minus alpha divided by 60. That's what we found in the first problem. So this is going to be negative. R is alpha. Plus alpha squared. We can take out an alpha. And voila. Now we have our v squared. We already know the moment of inertia around the center of mass, which was this. Okay. I'm keeping the 60 like this. I'm not adding up 1 because I can see that these two are gonna cancel out. Okay, so let's calculate t. So it's equal to half of the mass. In our case, the mass is 15m divided by 16 multiplied by v squared. Plus half of the moment of inertia around the center of mass, multiplied by the angular momentum squared, which is just theta, the derivative of theta, squared, obviously. Okay, so now we reduce this equation as much as we can. Let's just do that. So we see that we can isolate theta squared, alpha squared, m half. So it's going to look like this. There was a alpha square here. Obviously, there wasn't supposed to be any alpha square here because it's right here. So I just removed it. Okay. So this right here is the same as right here. So we can remove this. So we have 60 multiplied by 16, 960 cos theta, plus 15 divided by 16, plus 253 divided by 512. And we can calculate this. This is equal to 15 multiplied by 32 plus 253 divided by 512. This is equal to 733 divided by 515. This, this we can remove. This is minus 1 over 32 cos theta. And this is equal to minus 16 over 515 cos theta. So we can take out the 512. Divided by 2 multiplied by 512. It's 1024. And there you have it. That's the final answer right here. Okay. So the trick here is really just to break down your problem. First thing first, look at your equation and then figure out which information you're missing. In our case, it's the speed. And then break down the speed as the derivative of the position at the center of mass to a drawing, and then figure out which vector you need to add to get the position at the center of mass. So that was it for this number. Thanks for watching. I hope you got everything right, and I'll see you soon. Bye bye.